Chapter 8, Repairing the Rift. Quote, Art is the objectification of feeling and the subjectification of nature. Suzanne K. Langer. Can we resolve the issues that have led to extreme reductionist positions on the side of science and to phenomenology, hermeneutics, and proud humanism on the side of the humanities? Can we repair the rift? As I have said before, in considering the Cartesian position, one barrier to repairing the rift was the failure to bring consciousness into the worldview, to naturalize it. That has now become possible, and indeed there is mounting evidence from neuroscience that our cognitive capacities arose in the natural order as a result of evolution. Clearly, these capacities did not stem from logic or computation, but instead emerged from the appearance of various brain functions, including perception, memory, motor control, emotions, and consciousness itself. The brain itself emerged during evolution from a series of events that involved historical accidents. Since the human brain and its products developed within a historical context, one might say that the tracing of that development must to some extent include the same methodology as historians use to trace social changes or battles. That is, to some extent, true. But the theory of natural selection, because it is buttressed by molecular genetics and paleontology, allows a historical account of brain evolution that is somewhat more coherent than most descriptions of human exchanges in peace or war. In one of his essays, Isaiah Berlin makes it clear that the concept of scientific history is untenable for a variety of reasons. First, unlike science, history cannot be described in terms of general laws. This does not mean that historians do not rely on general propositions. They rely on multiple facts and on the general texture of experience, often involving common sense. There is, in general, however, an absence of the models that are so frequent in scientific pursuits. Moreover, the logic and hypothetico-deductive method central to science is not often applicable to historical events. Even though some claim may be made for such approaches in the human sciences of sociology and economics, they are not readily applicable to most historical accounts. If science is concerned with similarities and laws, history is equally concerned with unique events and differences that often depend on beliefs, desires, and intentions within a given culture. In considering human affairs, the scholar or interpreter must place himself or herself within the fabric of these propositional attitudes. General history is a mix of disparate elements that can be studied within different disciplines, but not in terms of some general law. Moreover, there are normative elements related to morals and aesthetics that are involved within historical descriptions. These issues pose daunting challenges to the historian, who may have to understand and interpret events that occurred in a culture other than his or her own. Berlin makes the claim that scientific and historical accounts represent different kinds of knowledge. He expresses this difference by contrasting the views of an external observer and an actor, a contrast between coherence and interpretation. While the gifted historian must be able to describe the doings of people in many dimensions, scientists on their side do not depend for their generalizations upon contact with common human experience. History, in Berlin's view, is not and cannot be a science. From time to time, individual historians have attempted to overgeneralize historical interpretation. These results can seem ludicrous. Take, for example, the efforts of Brooks Adams, Henry Adams' brother. In a book called The Law of Civilization and Decay, he attempted to interpret history in terms of the growth and decline of commerce, with less than satisfactory results. In more recent times, one may note the grand efforts of Oswald Spengler and Arnold Toynbee, both of whose syntheses have fallen by the wayside, and even Vico in his efforts to describe cultural stages in history as those of gods, of heroes, and of men, succumbed to overgeneralization. Not all attempts to describe and construe past events are so grandiose or silly. John Lewis Gaddis, for example, has put forth an excellent account of the methodology employed by historians. He is aware of the contingent, incomplete, and irreversible complexities of historical events. In describing approaches to deal with such events, he justifiably decries the linear, overly simplistic analyses of many social scientists. Effectively, his claim is that the complexity of history cannot be fit by a Newtonian model, and he rejects the notion of reductionism as a means of historical analysis. But then he suggests that what historians do is closer to the procedures of scientists. He bases this claim on the advances made by scientists in complexity theory, chaos theory, fractals, and the like, advances that he feels share the flavor of the historian's methodology. Unfortunately, the analogy has several flaws. First, although interesting results have been obtained in the analysis of complex systems, scientists are far from having an adequate picture of far from equilibrium or irreversible processes. We still lack adequate means for dealing effectively with multi-causal processes for which independent variables cannot be discerned. Second, the measurements made in deterministic systems that are chaotic are still physical measurements. Although small initial errors in such measurements propagate to yield chaos, they remain quantitative measurements. Historical systems are rarely, if ever, quantifiable in this way. Nonetheless, Gaddis persists in his analogy and respectfully disagrees with Berlin. The methods of historians he so artfully summarizes will remain largely qualitative. Gaddis makes a defensible claim that there are sciences with a historical flavor. These include cosmology, geology, paleontology, ecology, and anthropology. It is true that scientists in these areas must take account of historical events, and evolutionary theory and natural selection certainly must deal head-on with such events. One might even consider Darwin a historian. Moreover, because of their inevitable complexity and limitations on material, fields such as geology and paleontology must deal with incomplete records. Nonetheless, there are powerful scientific theories that constrain these fields: astrophysics for cosmology, plate tectonics for geology, natural selection for biology. No such set of constraining theories is available to historians unless one admits a potpourri of weakly based psychological theories, Freudian analysis, socioeconomic models of rational behavior, and the like. Perhaps the closest analog to Gaddis' suggestion is ecology, where multiple variables recursively interact in complex environments. Indeed, we may conclude that there are bases for calling ecology a soft science. But even so, ecology can still marshal a set of constraining scientific theories and quantitative methods not available to historians. If we accept Berlin's analysis rather than Gaddis's, we may ask why the methodologies and aims of science and historical analysis differ. The answer is not hard to find. Historical events are contingent, usually irreversible, and often unique. They involve high-order issues related to cultural idiosyncrasies, linguistic ambiguity, and specific moral or aesthetic constraints. While, as a person, a scientist is necessarily embedded in such a fabric, his or her aim is to supervene over or transcend the accidents of everyday existence and derive a general set of models and laws in whatever subject domain he or she works. It is of particular interest, however, that these laws themselves do not give rise to science. People pursuing experiments and hypotheses give rise to laws. Science itself, and clearly Western science, arose within a particular historical context. What factors govern the actual historical emergence of scientific knowledge, beginning with men like Francis Bacon and Galileo and going on to the present? I believe we can help formulate an answer to this question by considering how the brain evolved and how it operates. In the earlier chapters of this book, I mentioned the evidence that the brain and mind arose as a product of natural selection. I concluded that the human brain itself operates as a selectional system with highly variant repertoires of circuits. Subsets of these circuits are selected to match signals from the world of complex events. In a previous chapter, I argued that the brain is not a computer and that the world is not a piece of coded tape. The brain must, in the absence of unambiguous signals, establish regularities of behavior under constraints of inherited value systems and of idiosyncratic perceptual and memorial events. In human beings, such systems and events necessarily involve emotions and biases. Selectionistic brains themselves show the efforts of historical contingency, irreversibility, and the operation of nonlinear processes. They consist of enormously complex and degenerate networks that are uniquely embodied in each individual. Moreover, human brains operate fundamentally in terms of pattern recognition rather than of logic. They are highly constructive in settling on given patterns and at the same time are constantly open to error. This is seen in perceptual illusions as well as in higher order beliefs. But as shown by the analysis of learning, error correction is usually available in response to appropriate rewards or punishments. When we consider modes of thought pursued by selectionistic brains, there is a set of relations between pattern recognition and logic that is both contrastive and reinforcing. A fundamental early mode of thinking that is highly dependent on pattern recognition involves metaphor. Metaphor is a reflection of the range and associativity of enormously complex and degenerate brain networks. It is pertinent that the products of metaphorical thinking can be understood but cannot be proven as can simile or logical propositions. For example, if I say, "I am in the evening of my life," the statement is understandable but not provable. Language itself reflects the constructive yet inherently ambiguous and indeterminate aspect of this mode of thought. These features are the result of the trade-off between specificity and range in selectionistic systems that necessarily exhibit degeneracy, a subject I shall address in Chapter 10. The diverse repertoires of such systems are never perfect matches to the contents of the domains that they must recognize. But after selection occurs across a range of variants, refinement can take place with increasing specificity. This is the case in those situations where logic or mathematics can be applied. We conclude that the necessary price of successful pattern recognition in creative thinking is initial degeneracy, ambiguity, and complexity. In scientific situations, however, the subsequent application of observation, logic, and mathematics can yield laws or at least strong regularities. In the case of historical analysis, qualitative judgment and interpretation are usually the most we can achieve. Although all of our brain functions and cognitive capacities are constrained by physics and can be understood as products of natural selection, not all of these capabilities can be treated successfully by reduction. As a means to repair the rift, the notion of consilience, as proposed by E.O. Wilson, is untenable. His idea, for example, that normative systems such as ethics and aesthetics can be reduced to explanation by epigenetic rules of the brain is inconsistent both with the nature of these systems and with how the selectionistic brain works. As David Hume pointed out, ought does not come from is. To assume otherwise is to indulge in G.E. Moore's naturalistic fallacy. Looking at the issue from the side of the brain and mind, epigenetic rules cannot satisfactorily cover the rich complexity and individual history of degenerate networks in the brain. Conscious experiences themselves are enormously complex discriminations in a higher order qualia space, as we have pointed out, and each individual's history and set of brain events are unique. Although there are certain regularities of intentionality and behavior, they are variable, culture and language dependent, and enormously rich. Subjectivity is irreducible. There is a curiously recursive element in this brain-based account of how knowledge is acquired. To get science, we need history acting on selectionistic brains. Eventually, this allows the reduction of certain physical and chemical events to general laws. The world order or universe follows physical laws. The remainder of individual and historical events must also follow these laws, but cannot be fully explained by or be reduced to them. Irreducible or not, we can agree that all these events are scientifically grounded in the natural order. The evolution of brains and conscious minds occurred by natural selection within the framework of physical laws. So the sequence is clear. Following the evolution of Homo sapiens, the emergence of language and higher order consciousness allowed the development of empirical science in the service of the verifiable truth. The application of logic in relation to language and observation of the world, and of mathematics as the study of stable mental objects, profoundly enhanced these developments. Nonetheless, these developments occurred within a specific historical matrix that cannot be reduced to them or by them. Moreover, there is no contradiction in the fact that selectionistic brains capable of higher order consciousness and pattern recognition could create artistic, aesthetic, or ethical systems within particular historical and cultural conditions. We can conclude that there is no logically necessary divorce between science and the humanities, only a tense relation in which science is admitted as a fundamental but not exhaustive or exclusive basis for grounding our knowledge. This picture, which is starting point for brain-based epistemology, is considerably looser than the rigorous developments of epistemological issues by generations of philosophers. It does not, however, exclude these rigorous developments. Rather, it relates them to their ultimate origins in natural and neuronal group selection. In contrast to Queen's efforts at naturalization, brain-based epistemology does not stop at the skin or sensory receptors. It includes more than perception. Indeed, it is based on the analysis by neural Darwinism of conscious states. The neural underpinnings of such states make human knowledge possible. It is well to recall that even though all our knowledge depends on our conscious states, these states are necessary but not sufficient for learning. Conscious states themselves appear to have many of the characteristics of irreversible, contingent, and fleeting events. They are unitary but change serially in short intervals of time. They have wide-ranging contents and access to stores of memory and knowledge. They are modulated by attention. Above all, they reflect subjective feelings and the experience of qualia. The evolutionary advantage offered by the emergence of the reentrant dynamic core provided its possessors with vast numbers of sensor-motor discrimination. Qualia are just those discriminations entailed by different core states. They can reflect factual verities as well as illusions and are, in all cases, subject to the constraints of neural value systems. Given this picture, which is consistent with neural Darwinism, it is no surprise that rich private experience and external historical events should share properties of both contingency and necessity. The underlying historical processes have complexities that rule out simple reduction of all experience to scientific description. The remarkable event remains. Thought within such a system led to the scientific revolution and the generality of scientific laws. It is enough to show how both science and history can be comprehended in our picture of the brain. Divorce is not at issue. The processes that give rise to our understanding comprehend both the sciences and the humanities. Chapter 9, Causation, Illusions, and Values. Quote, reality is merely an illusion, albeit a very persistent one. Science can only ascertain what is, but not what should be, and outside of its domain value, judgments of all kinds remain necessary. Albert Einstein. In our attempts to trace and complete the Galilean arc, we must not abandon the aim of science. That aim is to possess a value-free, veridical description of nature, one free of illusions. Science, as the physical chemist Jacobus Heinrichus van 't Hoff once said, is imagination in the service of the verifiable truth. If we accept this, we must also accept that there is no necessary or restrictive constraint on how imagination is exercised, provided that observation and experimentation lead to verification. The admission of consciousness as a proper target of scientific research has a curious consequence. One must find means of analysis that do not deviate from the causal analysis employed in third-person research. At the same time, one must be aware of the fact that consciousness is a first-person affair, displays intentionality, reflects beliefs and desires, and is subject to illusions and abnormalities that are cousins to creative imagination. To see how to handle this situation, we must analyze the causal connections of brain action. We must then reconcile this analysis with the existence of illusions, useful and otherwise. First, however, let us take stock and review the argument. We have taken the position that, given the selectionistic properties of human brain, no adequate reduction of human sciences to the brain's so-called epigenetic rules is realizable. The brain operates by selectional matching of its nonlinear, variant repertoires with occasionally novel and nonlinear events provided by the world and self-signals. With the advent of true language and higher-order consciousness, enormous numbers of discriminations can be experienced. The degeneracy and associativity of these discriminations are accompanied by an even more enormous set of combinations and recombinations of states integrated by the dynamic core. These states are not necessarily vertical and in addition are often constructive, contingent, and context-dependent. The mode of thought that results from these operations initially involves pattern recognition and not logic. Because selection in this neural system is constrained by the operation of heritable value systems and perceptually based memory, the system entails intentionality, beliefs, desires, and emotional states. Such a system is a subject to contingent events from within as it is to external contingencies. It can exhibit singular states as well as regularities, and some of these states are experienced as private, irreducible features of subjectivity. All of these properties are expressed in one degree or another in thinking and in language. Early on in thinking, metaphor can dominate, and even after the application of logic, language is rich with metaphorical expression. Moreover, as Queen pointed out, language itself shows indeterminacy in reference and translation. The ambiguity that is inherent in natural language is not a critical weakness, however. On the contrary, it is the basis of the rich combinational power that we recognize in imaginative constructions. These properties are just what one would expect to result from the operation of a selectional brain. Scientific insight results from this power is constrained by logic, mathematics, and controlled observations. But not all judgment and thought can be reduced to scientific description. A key example is the area of normative judgment seen in ethics and aesthetics. Hume's argument still holds: ought does not derive in any straightforward way from is. These limitations on scientific reduction do not mean that conscious activity, language, and issues of meaning derive from some spooky realm of res cogitans. By explaining the neural basis of conscious thought, we can in fact reconcile the appearance of all of the rich properties of thought with physics and biology. The result is indeed a form of reconciliation. Divorce is not necessary. To provide a firm base for this reconciliation and for a brain-based epistemology, we must address a classical question. Are consciousness and mental events causal? And if not, what is the relation between causal brain action and consciousness? The answers to these questions may startle us inasmuch as they reveal a set of illusions that we must live with. It is commonplace to talk of mental events or phenomenal experience as if they were causal, but inasmuch as consciousness is a process entailed by integration of neural activity in the reentrant dynamic core, it cannot itself be causal. At the macroscopic level, the physical world is causally closed. Only transactions at the level of matter or energy can be causal. So it is the activity of the thalamocortical core that is causal, not the phenomenal experience it entails. To make the point clear, let us define C1 to be the integrated pattern of neural activity that makes up the dynamic core at a particular time. C1 entails a conscious state, we will call C, in which involves a particular set of discriminations. C1 not only entails C, but contributes causally to subsequent C1 states as well as bodily actions. The relationship between C1 and C is faithful, and for this reason, in most cases, we can speak of C as if it is causal. Indeed, C states are informative of C1 states. They are our only access to such states, inasmuch as our neurophysiological methods cannot, at present, record the myriad neural combinations that are integrated in a given causal core state. So we must conclude that our belief that consciousness causes things to happen is one of a number of useful illusions. The usefulness of this particular illusion may be appreciated by considering that we speak to each other in C language. But the underlying neural activity is what drives individual and mental responses. Philosophers have found this set of conclusions to be an expression of epiphenomenalism, that consciousness does nothing. In fact, it serves to inform us of our brain states and is thus central to our understanding. The traditional horror with which epiphenomenalism is met by philosophers can be abated once the faithful entailment mechanisms of reentrant core states are understood. I have called another conscious illusion the Heraclitean illusion because it reflects our way of thinking about time and change. Most people sense the passage of time as the movement of a point or a scene from the past to the present to the future. But in a strict physical sense, only the present exists. The integration of core states leading to conscious states takes a finite time of 200 to 500 milliseconds. This time period is the lower limit of the remembered present. The past and future are, in contrast, concepts available only to higher order consciousness. Nonetheless, we often think of the flow of time as we do in terms of the movement of a Heraclitean river. Within this illusion falls the changing sense of duration we all experience under different conditions. Experienced time, unlike clock time, can seem slow or fast depending on various conscious states. These issues may be connected to two others: the usefulness of conscious discrimination in planning over times of seconds to minutes, and the temporal relation between the activity of the core and a brain areas concerned with action and agency. As I have said, conscious states involve integration times of hundreds of milliseconds. But unconscious neural activity leading to action can lead to much faster responses. Many such responses, aside from innate startle responses, require conscious training. After deliberate practice, habitual responses are then mediated non-consciously and rapidly by subcortical structures interacting with the cortex. Clearly, it is the play between core states, attention, and subcortical responses that provides the basis for complex suites of action and movement. Connected to the illusion of a causal consciousness and the Heraclitean illusion is the time-honored and much-debated issue of free will. In the strict recognition that all physical events have causes, one must conclude that core states as physical events are determined. Nonetheless, when not physically bound or in prison or in the throes of neural disaster, we can honestly claim the ability to do as we like or see fit, illusory or not. It is on the base that we hold persons responsible for acts determined by society's oughts that we train our children accordingly in terms of reward and punishment. These matters are connected to the relation between normative concerns and neural states. We have dismissed the idea that ought comes from is and have repudiated the naturalistic fallacy. Nevertheless, we have all inherited a set of neural structures, the value systems that are critical to the functioning of our brains as selectionistic systems. As I pointed out earlier, the function of these systems is to provide species-specific constraints on the manifold of selective events that can occur in an individual. Suckling reflexes, startle responses, and the action of hormonal pathways and of autonomic neural systems affecting our metabolic and physiological states and emotions are essential to our adaptive functioning. However, they must not be confused with the categories that arise after experiential selection under their constraint. Indeed, in humans with higher order consciousness, the learning of categories can actually modify the set points of value systems. Humans, unlike most animals, have modifiable value. What ensues is not predictable. There are no animal equivalents of saints who, even under torture, can prefer death to renunciation. So value systems may jumpstart the building of oughts in a society, but do not directly determine them. Value systems also provide a brain basis for our complex emotional responses. Unlike Antonio Damasio in his excellent account of the neurobiology of emotions, I consider that emotions are complex states arising from core interactions with value systems. The C1 states that ensue are accompanied not only by feelings and cognitive content, but also by the bodily responses that these states cause. The pleasure and displeasure that can arise clearly reflect the activity of modulatory value responses. But just as C1 states reflect huge complexity, their interaction with value systems can also lead to enormous complexes of primary and secondary emotions with and without cognitive concomitants. All such responses are intimately coupled to the cognitive and emotional construction of the process we call the self. In this respect, whatever errors are laid at Freud's doorstep, he must be credited for his exploration of that process and his attempts to understand it. When we contrast the picture of generativity provided by brain-based epistemology with that of its philosophical precursors, we cannot help but be struck by a startling difference. What we have called traditional epistemology is concerned with justified true belief and the pursuit of truth and truth conditions. By no means should the importance of such concerns be underestimated, but their pursuit is, in the end, a narrow and terminal enterprise largely preoccupied with language, meaning, and logic. It has not been the proper concern of that enterprise to take up motivation, conscious or not, or emotion or pattern recognition per se. Nonetheless, these are all critical to how knowledge is acquired. Although the biologically based enterprise is considerably less elegant, it can be looked on as prior to the generative of the traditional view. A possible criticism of this conclusion is that it confounds psychology and epistemology. So be it. It is as important to human knowledge to know how knowledge originates in the long course of evolution as it is to understand truth by disquotition. If we concur that the statement, snow is white, is true, and only if snow is white is an elegant way of assuring a certain kind of truth, it is equally important to recognize its biological as well as its social origins. The reasons are compelling. There are various grounds for claiming truth, and these grounds must be placed in relation to their origins. To be restricted to invariance under lexical substitution, a property of first-order predicate logic, is to narrow a fate. Indeed, the development of logic itself must have depended on the cultural consequences of higher-order consciousness. Creative conscious imagination, complemented by logic, has gone a long way in the development of scientific truth. It is therefore illuminating to ask how creativity in thought and action emerges from the operation of the brain as a selectional system. Chapter 10, Creativity, the play between specificity and range. Quote, the mind of a man is more intuitive than logical and comprehends more than it can coordinate. Luc de Clapeyres, Marquis de Voisinargues. In discussing creativity, I wish to exercise caution and restraint. My purpose is not to discuss aesthetics or the specifics of artistic creation. It is rather to ask how a selectional brain theory provides a useful background for understanding individual and communal acts of creativity. The word creativity itself has rich connotations. To be creative is, by dictionary reference, to be original, inventive, expressive, or imaginative. To create is to make, produce, construct, or call into existence. A reference to God the Creator is not rare in certain contexts. Less obvious is the implication that a creator has freedom to create, connecting the various aspects of creativity to problems of free will. As I said, I want to stay away from these issues, and therefore it may be asked why I turn my attention to the matter of creativity at all. It is because I believe that a case can be made that understanding a brain operating by selectionistic mechanisms to yield a consciousness composed of enormous numbers of discriminations can provide an underlying basis for creative actions. I want to be careful, though, in pursuing this issue. The tenets of neural Darwinism are not to be considered the proximate or even ultimate explanation of our ability to create in whatever field, but they can cast light on the problem of how conscious and unconscious brain activity can give rise to new ideas, works of art and music, and literary productions. In such works and productions, we reveal a second nature. If our scientific description of the world is concerned with nature, our creativity reflects the ability of our brain to give rise to a second nature. This is the case because of the way in which the complexity of the brain's repertoire can be selectively matched to the complexity of signals from nature itself. I have said that, if the assumptions of neural Darwinism are correct, then every act of perception is to some degree an act of creation, and every act of memory is to some degree an act of imagination. Remember, in addition, that the mature brain speaks mainly to itself. Dreams, images, fantasies, and a variety of intentional states reflect the massive recombinatorial and integrative power of brain events underlying conscious processes. Without impinging on the problem of free will, we can certainly see how neural Darwinism and its extended theory of consciousness provides the basis for such combinatorial activity. First of all, a selectional system must rely on the generation of diversity. The repertoire that result must, in general, contain very large numbers of variants. A good example to illustrate this point is provided by the immune system. Even though each individual might have the ability to generate different antibodies, if only hundreds or even thousands of variants were produced, the system would fail to recognize the variety of foreign antigens presented by viruses and bacteria. In fact, the number of different antibody variants, one on each separate lymphocyte, exceeds 100 billion. Beyond some upper limit, however, the cost of producing orders of magnitude more antibodies would yield diminishing returns. Antibody repertoire of adequate size also show degeneracy in their components. A given foreign antigen can be recognized by more than one structurally different antibody. Such a system is not built by information transfer from the objects it ultimately must recognize. Instead, it responds to them by differential amplification of selected variants. Similar notions are applicable to the brain as a selective system, for neural circuits and dynamics do not, in general, have prescribed information on what the brain will recognize by perceptual categorization. Of course, even in brains, there are evolutionarily determined value systems and reflexes characteristic of a given species. These constrained selection events in response to external and internal signals do not fully determine them. In a number of its responses, the operation of the brain is reminiscent of the statement by E.M. Forster, who reportedly said, "How do I know what I think unless I see what I say?" What has all this to do with creativity? In generating a rich repertoire, only a certain degree of specific recognition can emerge if, in building the system, no information is provided on that which is to be recognized. So, if instruction is precluded and yet recognition of a wide variety of states is required, the price paid is a certain loss of specificity. That loss, seen for example as ambiguity or indeterminacy in language, is the price that must be paid and the range of signals to be responded to is large. We know in fact that the eco-niche in which animals must survive has an enormous number of signals to which an individual must adapt. For individuals and species to survive, a trade-off must be made between specificity and range. Similarly, after the range of a brain's or immune system's repertoires is utilized, mechanisms must exist for going beyond the initial selectional steps. The differential amplification of initially selected repertoire events must be subsequently refined. In the immune system, this is achieved by mutating and reselecting already selected cells to produce antibodies with a higher binding energy to the foreign antigen. In the brain, of course, this means of enhancing specificity are quite different. The brain relies on a number of mechanisms to enhance the specificity of its responses. One involves experiential selection through changes in synaptic strength, constrained by the activity of value systems. The contrast between specificity and range clearly emerges during learning in the change from initial exploratory responses to later conditioned responses. Another source of specificity rests in the mechanisms of attention, which restrict particular patterns of neural response while bypassing others. The number of possible combinations of corticothalamic patterns of responses is hyper-astronomical. The mechanisms mentioned above can be combined with those of short-term working memory, of phone numbers, for example, or of long-term episodic memory of life events in the past to yield outputs that result from repertoire interacting exclusively within the brain. The important point is that this selective system allows enormous combinatorial freedom for thought and imagery, and even for logic and mathematical calculation. Sequences of thought can be presentational, as in the linkage of visual images, or discursive, as in thinking based on language, where imagery is not necessarily involved. In this account, thought reflects the activity of sensorimotor brain circuits in which the motoric elements are paramount but do not eventuate in action. Although the linkages and sequences during thought involve activity of motor portions of the cortex, the motor cortex itself does not send consequential signals to the motor neurons of the spinal cord or to the muscles. I have already mentioned my belief that there are two main modes of thought, pattern recognition and logic. I have also suggested that the primary mode, giving enormous range and confronting novelty, is pattern recognition. This is seen primitively in Gestalt responses, in the ordering of words, and in various acts of classification. It is enormously powerful, but because of the need for range, it carries with it a loss of specificity. In certain instances, logic can be employed to eliminate ambiguity. Of course, the use of controlled scientific observation enormously enhances the specificity and generality of these interactions. This movement from range to specificity may be seen as mirroring the generative relationship between brain-based epistemology and traditional epistemology. We may now return finally to the matter of creativity as a reflection of selectional neurosystems. There is enormous freedom for recombination among core states in humans having higher order consciousness. Creativity in any field must be permissively allowed for within the huge range of discriminatory qualia. The constraints that are applied through experience and convention prompt various internal experiments to emerge, involving order and disorder, tension and relaxation, and the play between the core and the non-conscious portions of the brain. Of course, the resulting output is subject to further constraints that come from experiences within a culture. These experiences determine the choice and response to patterns, altering expectation and prompting abstraction from the flux of experience. Many of these creative responses depend on the constructive nature of brain action. This can be seen in the denial of reality that emerges from neuropsychological disorders like anosognosia, which I shall take up next. Unlike the requirement that error must be removed from a computer program, however, the likelihood of error must be tolerated even in the normal individual if the brain is to confront novelty in an adaptive fashion. So it is no surprise that the very origin of Western science depended on the prior existence of certain norms and beliefs that science itself could neither verify nor show to be an error, even after its triumphant emergence as a major source of truth.